if you think about Node and programming JavaScript and taking a microservices approach to the architecture, it really, as programmers and architects, gives us an opportunity to create truly mind-numbingly horrible systems from a sysadmin's perspective. Sysadmins all over the world jumping out windows at the idea of trying to control all these different systems. Stepping in shot. And what we found when we're working with people is that actually, if you take this approach, you can make things work more efficiently. You can make things, you can deploy things more quickly, and you can make mistakes an awful lot more quickly. You can destroy your systems an awful lot more quickly. And it's that bit where the programming side meets the live and deployment side, the DevOps has, that line is blurred a little bit, and we have to actually think about that as developers now properly, in a different way than we did. So there's all sorts of problems, and the second slide here, I'll just give it away, it reads that deployment is not a trivial problem. And I want to introduce somebody who's going to make all those problems go away forever. A man who needs no introduction, but I'm going to do it anyway, is Peter Elgerv. He's our chief engineer. Come on.
Thank you, Paul. A rather begrudging and churlish introduction. Very kind. As Paul said, my name is Peter Elgerv. I work at Nearform, and I want to talk to you guys tonight about something called Nscale. And Nscale is an open source project that we've been working on at Nearform for a little while now, really to solve some of those deployment problems that Paul was talking about. So hopefully what I'd like to do is kind of dig into some of the issues and then run through the kind of principles and requirements that we have as a consulting company to solve and why we chose to build something like this. Feel free to butt in at any point and ask any questions or even further proofs, whatever you like. And I'll do my best to answer those questions. So just before I start though, just a big shout out to a few guys that have been very instrumental in working on this. First of all, to Matteo, who's been working incredibly hard on this. Also Chico and Mache. Those guys have worked incredibly hard on developing this project today, so a big shout out to them for their very hard work on this. I'm just a guy that's talking about it right now. So, as Paul said, the first slide, deployment is a non-trivial problem. It really is a non-trivial problem. As Paul said, a lot of us come from the backgrounds of kind of through C and Java and all that kind of stuff, and we've kind of, if you've been any time in the software industry, you come up against problems with deployment. You're not just in the box developing code, you have to put your code out into production, and when you start putting it out into production, you start to hit a bunch of other issues around scalability, around how you manage your code in production, how you manage your applications. And these are non-trivial issues, and they can be very, very powerful business-affecting issues. So here's an example. I don't know if you guys may have come across this one before. If you haven't, I'll just talk to it a little. Have you heard of a firm called Knight Capital? Have you heard of the Knight Capital story before? One of you guys. Okay, so Knight Capital were a high-frequency trading house system company. On August the 1st, 2012, they started with a net trading position of 350 million plus. And on that day, they were deploying an upgrade to their system. Now, their system consisted of 8 servers, and their deployments were manual. So the deployment was done with, by humans, by people actually typing in commands and writing scripts. I don't know the full detail. There's actually a full detail of this SEC report here. Now, there was a mistake made in that deployment, and the mistake was that the new code was deployed to 7 of the 8 servers. Now, whatever condition that caused to happen in the 8th server, it caused it to start sending rogue trades out. And those rogue trades became apparent very quickly, because what happened was they started to lose money very, very quickly. Now, there was no rollback, there was no automated rollback, there was no control over the system, it was all manual. So, if you can imagine, for a second, if you will, and I don't know how many, I certainly have been in this position, and not quite with the sum of cash, that sinking feeling in your stomach when you realise that you've just knackered up your deployment in some way, and people now can't get to your site, or the company you are now working for, you're employed by, is now losing money every minute that your system is down. I've certainly felt that sort of feeling before. It's not a good place to be in. You imagine the pain these guys were feeling at that point. So some diagnosis was done, and a rollback was attempted. Unfortunately, the rollback had the effect of amplifying the problem and increasing the training frequency of all 8 of the systems down. They ended up at a net loss of about 440 million on the day. The company went bankrupt, and there's a full report in that SEC finding there. So, deployment is a non-trivial problem, and it's certainly a business-affecting problem if you don't address it correctly. Now, that's not to say that every deployment mistake that occurs is going to be quite of that scale, but if you've been in this business for any time, you will certainly know that sinking feeling, that kind of sickening feeling that you made a mistake in deploying. So, there are a number of issues with traditional deployment. And when I'm talking about traditional deployment, what I mean is the kind of manual, half-scripted, half-human intervention type deployment. Deployment that you do where you have kind of a plan that's maybe written down on paper, or it's written in a file, or you have a bunch of guys that work through the deployment. It's always going to have some kind of human error in it. You're going to have inconsistent state. You've kind of got a fuzzy status. You're not really sure which state all of your systems are in. You think that they're okay, but you're not entirely certain. You've got to have a DevOps team running all of this for you. So it's a huge resource cost for any company as well. We've certainly faced these problems in Nepal. We've come across these problems, and we've had to address them ourselves in a number of ways. Just to give us a bit of background, we've got about 50 production systems in Node.js to date. We originally started deploying as a company primarily to infrastructure as a service, primarily to Amazon, AWS, and most of that was scripted deployment. That's not to say we haven't used passes. We have used pass systems before, so we wouldn't use API and also Heroku. And they're fine as far as they go. There are certain limitations to them as well, as I'm sure you guys are aware. Recently, around the turn of the year, we adopted Docker as our preferred deployment mechanism. Really because we wanted to get more control over our deployments, and we wanted to kind of reap the benefits of containerization and standard deployment. Now, of course, we went at that in the way that everybody else does, is by writing scripts. So we wrote Docker files, we wrote scripts, build scripts to create those containers, and we wrote scripts to deploy them out onto our infrastructure. We did that a few times, and it was quite successful for us, but at the same time, we didn't want to keep reinventing the wheel. And that's why we started to look at how we could maybe wrap this up into a project that we could use again in the name, and also maybe get some traction with you guys and with other people in the open source community to feed onto this, because one of the things that, and I think this plays very well into the whole kind of microservice theme, is that there's a huge benefit from breaking things down into smaller units. When you have large units of code, you've got a huge amount of testing to do, and there's a certain amount of, if you've been together a while, you'll know there's a certain amount of fear to that deployment because you've got a big unit that's going out. When you've got smaller units that you're working with, you can have more confidence in them. But the problem is, you've almost traded one set of problems for another set of problems. That other set of problems is the management of all of those small units of code that are running on your systems. So, having faced those problems, we decided to start building Nscaler, which is our open source deployment tool. We have it now, it's released. Please go and Google it and have a look at it. And I'll take you through some more detail over it in the rest of this talk. So I guess really just to talk a little bit about the requirements that we have for Nscaler. And I think these requirements were really teased out over a number of months as we've been working on various projects. But one of the key things for us was the ability to roll the system forward and backwards. Rollback being one of the most critical things. It's really important when you're doing deployments to have a button that you can press It says, take me back to where I was. Something screwed up here. We don't know what's going on. We broke the code. Please take me back to a known state. And that was one of our key things, is that we could go back to a known state of the system and then figure out what had actually gone wrong back in testing. So that was one of our key things. The other thing was to really capture knowledge about our deployments, to really understand and isolate parts of the system in containers, and to then understand the history of the system over time and how the system has evolved. Because as you know, systems evolve over time. You add pieces to them, you remove pieces. I've often heard, there's a quote, I can't remember who said that software engineering is a little more like gardening than it is like engineering. You try bits out, you change things around, see what works. That's true to a certain degree. And so being able to capture how a system changes over time was important to us. Another use case we were very interested in was system replication. How do you take a running system, which might be your production system or development system, clone it into another environment so you can run maybe production tests or do something with it that you don't want to do against your production system. So that was a really important use case for us as well. And the other piece as well, being a consultancy, was that we wanted to drive efficiencies in the business. We didn't want to put a lot of our energies into DevOps. We want to put a lot of energies into development and adding value to our customers, and to capture the ability to deploy and maintain systems in a very controlled way without having to kind of repeat scripting from scratch. So those are our kind of key requirements, and those kind of were teased out over a while as we were developing systems. So we would just sit down and write these down, right? This came from experience. So based on an understanding of what our requirements were, we started to develop N-Scale, and there are really three key principles that N-Scale is based on. Those are immutability, homeostasis, and containers. The three big words, so I'm going to just spend a bit of time explaining what I mean by those three terms, and how they all interplay in N-Scale. So, first of all, immutability, which sounds like a bit of a strange term to apply to a live running system, because the system is going to change over time. What I mean by immutability at a system level is that the description of the system, or the overall picture of how a system is put together, is immutable, and that you move between immutable revisions of a system using that system description. So whilst your servers and what's running on those is going to change and is mutable, the actual description of that system is immutable, and as you change it, we have a revision history of all of those changes to the system. So that sounds a little bit like a Git commit log. You'd be right, that's exactly what we use. What we do is we describe the system using a set of JSON documents, and then we put those JSON documents under version control. And every time there's a mutating change to the system, so let's say if someone builds a fresh container, or updates or modifies the system topology by moving a container, that change is then logged in our Git repository, so we can see how the system has evolved and changing over time, and also who's made those changes to the system over time. So that's a really important feature for us. It's absolutely key, and it enables a couple of things. One of the key things it enables is the ability to roll back, because if you have an immutable log of changes to the system, then rollback is really just jumping from revision 1 back to revision 2, or whichever way around you want to put it. So that's one of the key and critical principles that we've based N-Scale on. I'll just give you an example here. This is a list of revisions. So I'll run some commands later and let you guys actually see the system running. But here we've got, I'm just listing revisions for a particular system. As you can see here, all the commits by me. But as you hear, here's the first commit to the system. And I've changed the actual system definition at some point here, and then I've built some containers. And as I build those containers, each container build is logged as an immutable change to the system. Okay? Homeostasis. So we're describing the state of the system. We're keeping that in an immutable revision log. So the head of the system describes exactly how we want our system to be deployed. So that includes things like what is the load balancer that we're using? Are there any security groups in there? Do we have auto-scaling groups in there? What are the VMs that are part of that system? And how the container is distributed across those machines. So it's a description of the entire state or the desired state of the system. Now, as you know, the desired state is not always the running state of the system. So one would expect after we've deployed the system that the desired state matches the actual running state. But let's say the container crashes. If a container crashes or a machine crashes, then those two pictures no longer match. Okay? So what we do in N-Scale is to analyze and provide an analysis tool to look at the running state of the system. So what that will do is go out, it will look at the machine instances, it will actually query the containers running on those machines and pull back a system definition. That definition,
just because it's topical, how would that have reacted to today's Amazon craziness of tearing down their cloud in bits and rebuilding? Can you just include it in what you're saying? Sorry.
Sure, yeah. Well, so Amazon's craziness today is just going around and just randomly, well not randomly, but rebooting stuff, right? So the impact on the system would be, there could be a larger impact because normally what we do is we run a management system within Amazon. So if your management system is rebooted, you need to come back into your management system, but then if other instances are down, you can make a comparison against those instances, okay? Now, there's a lot of there's a few technical details around that because when the machine comes back up, the instance ID is going to change, there's a whole bunch of instances, identifiers that will change. We take care of that most of the time, so we can match up those instances against what we think the running state of the system is. So in the event that you do have a machine go down and come back up again, and those containers are brought back up, then we can still run a diff against the running system. But I didn't try it yet against the Amazon outages today. So getting back to homeostasis, the theme of homeostasis, the idea is to constantly analyze the state of the running system and produce diffs against what your intended state is. Given that we can create a diff between what our desired state is and what the actual state of the system is, we can then generate a set of instructions to bring the system back into line with what we think the state of the system should be. So if you think of it, it's a little bit like a room thermostat, right? So if the temperature goes too high, it'll turn the radiators off, and it'll drop right down, and we'll go below the actual desired line, the temperature will come back, the radiators will come back up, and we'll kind of get this oscillation.
Does that not mean it's mutable? Are you changing the system while...
No, so what we're doing is, the concept of immutability is applied to the description of the system. Okay, so the description of the system is a set of JSON files. As those change over time, you might pick a particular version and immutable revision. That is the desired state of the system. So what we're doing is we're comparing reality against the desired state in order to give us that homeostasis effect. Okay? So, and I'll run some of these commands later for you, but here's an example, right? So, we run a system check. Okay, so NSV system check. That's detected that there's a deviation from the deployed revision. In this case, what's happened is I've actually just gone in and killed the container. N-Scale has detected that that container has been killed and has come up with this plan. This is the plan to put the system back into the state that it should be. So you'll see that there's kind of a high-level plan there, and then what we're showing here is the actual commands that we've run against the system to bring it back into the state. Against that particular host, we're going to go in and start that container with these arguments. We then run a system fix command. The fix command goes off and executes those commands, brings the container back up, and the system is brought back into line with our perception of what the system should be, what the reality should be. So the thing that enables both homeostasis and immutability is the concept of containers. And I'm sure show of hands, how many people here are familiar with Docker? So a few, okay, cool. How many are running Docker in production? One. Excellent, okay, good man. So containers and the whole Docker wave is what really enables this. Because we can treat our software components that we deploy as very similar units, rather than having to have custom commands for every piece that we deploy and custom bespoke scripts for everything we deploy. Because we can treat them in the same way, we can apply these concepts to a system. So in Nscale, what we've done is we've taken that concept a little bit further, and we now treat our entire systems as a set of containers. So what I mean by that is that a load balancer is viewed as a container. That might contain a security group. That security group might contain a set of machines, and those machines will then in themselves contain a set of Docker containers. So by making it containers all the way down, and by logically thinking about containers as the same units, we can think about systems in different ways, and that enables us to build this homeostasis and immutability into the system. So here's just the output of an Nscale command, which is listing the containers for a particular system. So if you can, I'll just pick this up for you. At the top there we've got a load balancer with its nice long DNS name there. We've got a machine instance. We've got a security group, and then we've got 4 Docker containers. One is a web front end, and then we've got 3 other services that are being talked to spoken to by the web front end in order to deliver the service. So that's our demonstration system. So the way we describe containers is using a set of JSON documents, and I'll just show you briefly this is the kind of detailed view of those containers. One of the things we're working on very hard at the moment is to improve the experience. So we recognise that editing big blocks of JSON is not really a good thing. And we'll be putting a release out very shortly that has a container description language, and would really appreciate any of you guys taking a look at that and giving us feedback on it. And I'll certainly be tweeting about that when that release comes out. But for now, this is the kind of machine level definition that we're using. So if you look at the top there, we're defining a machine. Now this is actually running, this is the definition that would run on my laptop, for example. There's a VirtualBox container there, and then beneath that I've got a web container, and that's using boot to Docker. And as you can see here, this container is designed to run code because it's got a repository URL in there. So that's referencing a Git URL. And then I've got a set of arguments on here. So if anyone's familiar with Docker, you'll notice this is actually the Docker command line that you put on a container to run it. So this is telling me to expose this particular port, run as a daemon, and execute this process. And there's a few other bits of housekeeping in there, like the build number, the actual way you can find the binary when it's been built, and the Docker image ID. So that's one of the first sections that we describe as just a set of containers. The second portion that we describe in our JSON document is the topology of the system. And what I mean by the topology is how the containers are laid out. So how the machine instance is laid out, how those machine instances are related to high-level containers like load balancers, and how are the actual software containers distributed amongst those machine instances. And it's very simple. It's really a very well-structured JSON tree. So you see here that I have an instance here. This is the machine instance, and it has a link to this subcontainer here. And you'll see this as a Docker image ID, the binary, the local tab, the local tag, and version numbers, and so on. So the topology is really just a very simple tree-based structure in which we relate the containers. The point of having that structure is it allows us then to run analysis and planning jobs against the system as a whole. So those are the three key principles. I'll just reiterate them again. Immutability, homeostasis, and containers all the way. So what I might talk about now is just give you an idea of the architecture of N-Scale and how we put it together. I'd like to do this because I'd really love some of you guys to go and take a look at the code and really kind of block it and send me pull requests if you feel like it. That'd be lovely. So when we were building it, we kind of looked at some of the best systems out there that we could see. We're all big fans of things like Redis, where you've got a server and you've got a nice text-based protocol. So we wanted to kind of emulate that. Okay. So the way we built this system is we get a system kernel or a system core. The core knows how to manage containers. It doesn't know the detail of the containers, but it knows how to manage containers. It knows how to create immutable revisions and track them, and it knows how to do diffs. But a lot of that work is hived up to specific plugins. The core is addressed through a simple text over TCP protocol, so you can actually talk to it through Telnet if you so desire. We then implemented a Node SDK over the top, and the point of that is to allow automation. So if you want to write automation scripts in Node, you can write them using the SDK. And because it's a plain TCP-based protocol, we would really hope that we may see implementations. In fact, we may ourselves have a need for implementations in Java or .NET or other languages. We'd be delighted if other people wanted to do that as well. On top of that, we then built a command line tool, and that's our main kind of DevOps interface into the system, is to run the command line tool. And we've also used that for scripting into things like Jenkins. So we have one or two clients that have automated build systems where we've been able to just script in, add bash scripting that executes N-Scale through this command line interface, creates containers, and then deploys them out into their staging environment. We've also implemented a REST-based API on top and a management dashboard for people that like those kinds of things. One of the key things for us was also to make the system extensible, and our approach to doing that was kind of fairly standard, I guess, was to create a plugin-based structure. We support, the system supports two types of plugins. The first type is analysis plugins, and the second type is a container type plugins. So an analysis plugin should be able to go off and build a system definition. We currently have analysis plugins for local Linux, local Mac, and AWS. We then also have container plugins for Docker and the Amazon family of containers. So that would be load balancers, security groups, and auto-scaling groups. So the intent is that as we grow the system over time, we'll be able to add in containers for backspace, whatever iOS platform that we have a need to run on, or anyone has a need to run on. And there's a clean API, fairly clean API, you can use to build those containers.
How does N-Scale talks to Docker? Does it do it through the socket HTTP API or through the command line?
Good question. So there's a couple of ways it talks to Docker. If it's local, then it will talk to, it will look for the Docker host environment variable. Okay. Otherwise, it will try and talk to the Unix socket that's available. And that's local, right? Remotely, we chose to use a different technique, and the reason is that we didn't want to force people to actually make changes to their Docker configuration. What I mean by that is that if you run Docker on a so you've got a management instance and you've got 3 or 4 AMIs, let's say, that are running Docker. We didn't want to actually force people to have to open up ports on those AMIs or create custom security groups. So what we actually do is we tunnel through SSH onto those boxes and then connect to the local Docker socket through that tunnel. Because we actually wanted the experience and the developer and server experience, I think, has to be as simple as possible. And that's why we chose to do that. So you don't have to do any custom configuration. It's just a default Docker install of the runtime on the instances that you're managing.
Do you know if Docker plans to open the socket, or they plan on keeping it local?
It's more a question of actually having to set security permissions on your instances.
But Docker is kind of independent of that, right?
Yeah, I mean, whether that's open by default or not is irrelevant. The point is that you would have to get people to actually set security rules on those instances, okay, to open that port to then talk to remotely. All we assume is that you have SSH connectivity. That's it, and that has to be the base level for us.
It's a bit of an assumption, right?
Do you have SSH connectivity? You're going to have to assume some level of connectivity at some point. Otherwise, you can't do anything.
Sure.
So
SSH is...
we figured that SSH was probably the best.
In an system.
Yeah, absolutely. But we have. You have to connect in some way,
Sure.
right? So if you spin up, the default security configuration is usually you have SSH. Because most people boot up the server, they expect people to talk in some way. Usually that way is SSH. If you can't connect to it at all, then you're pretty much used to it, right? So that's the reason why we chose that. Is that better? So yeah, moving on from architecture. So I spoke about the open program environment. So what I want to do is just talk a little bit about the actual working deployment process. I've probably touched on this already, but just to kind of reiterate, the way Nscale works is to pull code from your Git repositories. So this is your development code. We also will be putting release out shortly. We'll pull stock containers from the Docker registry as well. So if you want a Postgres server or you want a Redis server, you can just pull those containers in by changing your system configuration. It will then build those software artifacts and give you a set of images. Each build results in a change to the revision history. One of those revisions is the actual deployed revision, okay, and that's marked as such. And then there's a deployment loop, and that deployment loop is to analyze the running system, compare it to what we think the deployed revision is. If there's no diff, we're done. If there is a diff, then calculate the plan, work out what the plan is to go from reality to what we want the system to be, and then execute that plan to deploy those containers out. So that's our kind of deployment loop. So there's two sides to it. One side is the ability to pull and build containers easily. The other part is to actually have this deployment loop and this deployment cycle. Now, the way we use it at the moment is generally to type those commands, to actually type in an analysis, type in a comparison, and then run a deployment. But we are moving to a model now where this is scheduled. So run a check every 5 minutes, run a check every 2 minutes, whatever frequency you want to run, and then correct the system whether the deployment should be necessary.
I was going to ask you about that. So this is, it looks exactly like the previous loop we talked about with comparing the running system essentially to itself.
Exactly. Yes.
In the homeostasis part, in the fourth point you talked about applying your plan.
Yeah.
Is that an application done, but from the command line it looks like it generates a plan which requires human intervention?
No, sorry. So the reason for showing the actual steps is because we felt it was important for sysadmins to actually see what was going to happen to their systems. You don't actually go and execute that plan.
But that's what I'm saying, the homeostasis part of it doesn't actually execute the plan.
Oh no, it does execute the plan.
Okay.
So you don't actually have to go and type those commands.
Yeah.
it will those commands are executed for you. The view of those commands is purely just for comfort. So,
and that does, I mean, that does create the possibility of loops. Of loops, perhaps. If, for instance, a change in the system, there's a difference, and then you end up applying the change.
yep.
But if you ever end up with a position where applying the change causes the original problem, you end up in a loop there. So, for instance,
yes, that's true, right? So let's say, for example, that's very true, right? So if you have a container that crashes on boot, so for some reason someone's put some particular in there, and it just won't run.
Theoretical scenario.
Theoretically, yeah, I've never done that before. But let's say, right, and that's exactly true. So what will happen in that case, if you've got this automated loop going on, is that the container will come up, it will crash, you run an analysis, it'll spin up again, it'll crash, right? And that's part of what I was referring to in our kind of automating this, is that there has to be some kind of alert mechanism on that as well. You know, so it's like spin up 3 times, then call a human, because things are not working. Right? So you're correct, there is a possibility of things like that, but I think that we're putting quite a lot of thought into how we would address those looping conditions and how we would, you know, when you alert a human about this. You alert a human every time, right? But when you really alert, like through SMS or something like that, do you know what I mean? So, yeah. Is that okay?
Yeah.
Okay, so I guess just to give the context, you guys probably already have this context already, but the way we run it is we have a management server which is running the builds, deployment and monitoring, and obviously we've got VMs running across various tiers, each of which is running containers. But the key thing is that everything is containerized. So everything is a container, everything is running in a container. We're not scripting anything out. There's nothing that's done that's not running in a container. And it's the power of having those containers which enables tools like Nscale to exist.
Sorry, Peter. Do you have like one microservice per container, or how do you split that?
Yes, that would be our general approach. Would be to have one service per container, so one process or one service per container. It's the kind of unit of technology. That would be our approach, for sure. There's a whole other piece around discovery and balancing and all that, but that's kind of
In a simple situation, you have one
service per service. You don't have to do that. I mean, you could imagine having an entire API sitting in a container, but we would generally want one process.
So you take out the container and the paste container with the server.
Exactly that. Okay, so what I might do now is just run a few commands and show you Nscale in action. For anybody who wants to have a go or play along, please go to this URL here. There's some workshops that we have on Nscale. I'd be delighted for anyone to have a go, break it, kick it around, and give me some feedback. But what I might do is just drive a couple of things now for you.
Yeah, guys, I think we're probably going to tweak that URL, and we'll probably tweak the reference to the Mike Capital story as well in a while. So we'll do it with a hashtag Node Dublin. Okay.
Yeah.
Peter, are you guys talking about tens of containers in the sort of systems you guys are working with?
Absolutely,
or hundreds,
or
sure. Like what sort of scale?
At the moment, we're talking about tens of servers, 20 size.
Containers?
No, services.
Services, but each
so it depends on the side of the system how many of those containers you need to scale up with.
Yeah,
but that's the kind of.
So tens of services. Okay.
Yeah. So can you guys see that? I need to maximise that a bit.
Or a lot.
Or a lot.
Yeah.
Hold on 1 second. Does that help?
Yeah.
Okay, so actually just clear the screen now. Okay, so this is LSD running on my Mac. Actually, I'll bring that a bit further away. So I've got one system. So what I've done is just told MS to list the system, and I've just got one system running locally. This is the startup dev block. You might have seen the startup dev block before. I'll just show you it running here on localhost. There it is. So this is the startup dev block. It tells you how long your startup has to live, based on a number of parameters, like your monthly revenue, your monthly expenses, and if you change one of those parameters, we're going to die a lot sooner, okay? So you might notice that on the startup dev block, there's a mistake. It's the startup dev click. So what I'm going to do is I'm just going to go and fix that. I'm going to rebuild the container and then deploy it using Nscale. So if I just edit that, you guys can't see that, can you? Is that better? Okay, so we're just going to put fix in now. Okay. So NSD. So we'll do NSD container list. So those are containers that make up the startup dev block. And the fix I put in was in the web container. So what I'm going to do is going to rebuild the web container. Yeah. Sorry. So what Nscale is doing now is just putting the changes to the repository. It's now running a build script. And that build script, in this instance, all it does is it does an npm install, copies the files. It's now built that into a Docker container, and it's just exporting that container. It might take a few more seconds to do that.
Are you modifying containers from base images to Docker containers at this point?
Yeah. So part of the setup for that repository is to create a Docker file.
Yeah.
And there's a very standard Docker file that has for Node, for example, it just has the Node dev images, a few other bits and pieces. It's pretty standard stuff. Right? And all we're doing is building a container. Okay. So that container is now ready for deployment. So if I now do an NSD. Okay, you'll note that this is the container I've just built here at the top of the revision history. So that's the mutating change to the system. This flag here tells me that this is the one that's currently deployed. So in order to put that fix out to the system, I'm going to just deploy that revision. Okay, so we deploy that revision. What that's done is actually stop the current running container and brought up the new revision of the system, which has the updated container. So if I now go to start dev click, it's now started the clock.
Can you look at this between?
Yeah. So if I look at the revision list, so actually what I might do is just show you the GUI. So it comes with its own GUI. I prefer the command line myself, but there you go. So this is showing me now that there's a pseudo root node here. Okay. Then there's one machine instance, and there's 4 containers running on that machine, right? Which is the web and the other containers there. And then if I click on the revision tab here, you can see the history of the time. But that's exactly the view that you're getting here, right, in the Revisionist. Okay, and for my next trick, what I might do is just increase the...
How's the graphing? How's that kind of graphing? You have a very complicated system?
Sorry?
Like, you have a simple kind of system where you got like four
Sure, yeah.
or 4 containers. But when you have a really complicated system, how does that look? Or is it kind of
Messy.
Messy.
Yeah, again, it's one of those things that we...
It's no big deal because the command line's going to do that anyway.
As you get to more complicated systems and more complex systems,
yes.
so at the moment we have it on systems where that's enough.
Yeah.
Okay, so when we're dealing with containers, that's okay. As you scale up, I think it may be the case that you break it down into, so you manage a portion of the system, and another portion of the system. Okay, so it's not that you manage the entirety of the system, but it's gets too complex. And that kind of mirrors how teams work anyway, right? You don't have necessarily have one-line control for the entirety of the system. You might think it is.
That's actually showing you individual containers, right, rather than groups of containers.
Those individual containers.
Yeah, but if you had 10 web containers,
Correct.
for example, that would show you 10.
Yeah. So we need to invest more time in the GUI, I think.
Yeah.
It's the honest
It's all
answer, right?
random here.
Yes.
So.
Oh no, for sure, no, exactly. So what I've done now is I've just logged on to an Amazon instance, and we're running the startup death block here. And if I just show you the system configure, you see it's slightly different. The reason it's different is that now we've introduced some more containers. So we have a load balancer, and then we have 2 machine instances here, and we're running a web front end on one of those instances, and then we're running 3 containers on the other instance. So what I'm going to do now is I'm just going to do so we list the systems on there, and there's a startup death block. So I'm just going to run a check. Sorry, give it the system name. This analysis will take slightly longer because it's actually reaching out to those 2 machines and querying the containers. It's also querying the Amazon API to figure out which load balancers and so on. So doing a full analysis on the system. So it might take a few more seconds to run this. Once it's done that, it's going to run a comparison against the deployed provision, and it's going to tell us if everything's okay. And everything is okay, jolly good. So what I'm going to do now is actually connect into one of those instances, and I'm going to do, sorry. Okay, so I've connected to the instance, if you remember in this picture here, I'm actually connected into this instance here. These 2 containers running. So what I'm going to do is I'm going to kill one of those containers now. So I'm going to do. Let's kill the group server. Okay. Okay, and just to check. Okay, so that's dead. So I'm going to come out of that. And what I'm going to do now is just run the check again. And again, this is going off and doing a full analysis, so it might take a few moments to run the check. We'll give it a bit of time. Any second now, we should get a report back telling us that that container is dead, and here's the remedial plan to fix it. There you go. Okay. So what it's telling us there is that on that machine instance with that IP address, 172.30.097, you need to do this to bring the system back into line with the desired state. Okay. So we can do that very simply by doing the system fix. Type. Again, it's running the same process. It's running the analysis. Sorry.
Is there a way to add custom checks that are not Docker verifications? Like currently, I think that the n-scale checks if the Docker container is running.
Correct. Yeah.
Is there a way to tie like a Docker image with a kind of like HTTP check or kind of integration test that you can run?
Yeah.
Not right now.
Or even a higher level business.
Yep. But that's something that we could certainly put in. Absolutely. Absolutely. But right now, is everything up and running? Is the kind of state we're checking against. So that's now run the remedial plan. So if I just run a check again.
So, sorry. So do you run your node processes inside the Docker containers with something like a supervisor or like something that's going to spawn the node process if it crashes?
Okay, so that's up to how you structure your containers, right? So,
But if you do that and you're not careful, the container is never going to go down, so you're never going to...
Sure, yeah, absolutely. But it depends on how you want to structure. You may not want to do that, right? You may want to
have it go down.
And the overall goal is actually to go away from empirical and specific measurements like is this on or off, but actually look at the specific business attributes of a site, make sure the site is functioning from a business perspective, and then react based on that. Problems with that at that level. That's kind of the end goal.
Yeah,
exactly. That's a while away. Might be a couple of weeks away.
Okay, so that's pretty much all I've got for you guys. Just to recap, NCA is still a work in progress. We're running weekly release cycles, so we put a release out this week. We're putting a release out next week as well, and every subsequent week. We are currently focused on the developer experience. So, as I said, removing the need to edit those large JSON documents and to have a really nice way for people to define their systems. When we put that release out, I would approximate in about 2 weeks' time. So I'd really appreciate anyone from this group taking a look at that and giving us feedback on it and helping us to improve it. Very much appreciate that. And we're also very much open for contributions, pull requests, bug reports, documentation. People want to become committers on the project. We're open to all of that. So hit me up on Twitter, or get anyone from me a call up if you want to get involved. We'd be delighted to have you. That's all I have. Thank you very much.
Could I ask a quick question?
Sorry, questions? Yes, of course.
Let's say you have sort of data containers where you're adding to a Postgres database all the time and containerize that.
Yeah.
Does your scheduler allow you to maintain that, i.e. to run back?
So, and that's a really good question, right? I think the data containers is something we're thinking about very hard. I don't know the exact model of that just yet. I think there's a lot of thought that needs to go into that. I mean, with a data container, what we would do right now is externalize the data. So you wouldn't put all of the data in the container. It would sit on the external disk, and then the actual software, Postgres would sit in the container. But there are still issues with that. Well, even issues with like upgrading the software in the container and having supposed to be external. Data containers have changed a lot less frequently. The spot we're focusing on right now is the problem of containers change very quickly, which is your changing the software. The whole data tier, and it's fine for things like Redis, which is just acting as a cache, if you're using it, of course. Using those kind of containers is fine, but I think the more long-lived containers, we're still thinking through those problems. I don't really have a cogent answer on that.
I think that's an issue with Docker as much as
it is, yeah. But I think I think the whole community is going to have to think through those answers, right? So, absolutely.
And just another quick one: does your system help keep it clean? So, if you've got hundreds of these containers crashing for some reason, have you something to run to remove those containers ultimately?
Yeah, actually, what we do is we actually run a housekeeping. So when we deploy a container, we actually run a housekeeping script at the same time, which purges out some of the data containers that are sitting in our system. Because we've got core cover times with Docker filling up the disk, so we built that into the system. We just said, okay, if we're deploying a container, take some of the cruft out. Now, I think we have a little bit of work to do on that, because rollback is really important, right? So how far back you go with the issue is a question. So you can do the kind of crufty name containers which are sitting around, but also the actual named or containers that are sitting, or images that are sitting there. You need to think about how many of those you keep on your systems, because they'll fill the disk up to a certain point, but you don't want to overdo it. So what we're planning on implementing is kind of a sliding window of images. I think maybe 20 is going to be enough. What's that? Maybe too much.
Hi, sorry, I was just wondering, What happens with containers when you switch from state A to state B? So how do you switch container? For instance, if I have a product, right, and we're moving from A to B, and in a B I have to change the containers.
Yeah.
So then I use scale deploy. So what happens with existing ones? When do you actually switch the actual state?
Okay, so what happens is and there's a couple of approaches to this right now, and we're working on this as well, right, is that physically what happens when you switch containers is you turn one container off and you turn the next container on, right? So, which the leading, I guess, is that you have loss of service potentially, right, in doing that.
No, like it's a theoretical question at the moment. So
Right. It potentially can, right? So, and there's two approaches to that. One approach is to actually, so we have a couple of deployment algorithms, because the intention of this is that you have algorithmic-based deployment, right? So there's two ways of deploying right now, and we'll be bringing other methods into this. One way is I don't care, so switch the container on, off, switch the next container on, and we're done. The other is to actually say, take this system out of its parent, right? So you drain down the connections, switch the containers over, and then switch it back into the parent, which is a safe way of deploying, in which case you don't lose any traffic through the containers.
yeah, but even thinking about load balancer. So load balancer, for instance, is in front of all my infrastructure.
Yeah.
And if I want to, I don't know, change it.
Sure.
I know it's super. Like if you want to change it slowly, then you want to be able to build it, and then when it's operational, then you just switch it.
Correct.
That's
Yeah.
what you actually do.
That's exactly what we do. So the safe way of doing it is to say, we go up to a machine instance, okay, we pull that out of the load balancer. So say you've got five instances, you pull one out, switch the containers, okay, you push it back in. Once that one's done, then you serially replicate that over the other machine instances. But the other way is you may not care, right? You may actually not care. The loss of may not be important to you, in which case you just deploy and switch.
But the other thing is as well, when you talk about the data layer changing less frequently than the logic layer, it's the same with when you've got an engine X load balancer in front, you're going to be upgrading that much less frequency than your business logic behind it that needs to plug in. So kind of it's more often you're going to go into a scenario where you're training in your load balancer and then bring it back up rather than trying to actually bring in a load balancer, which is a different type of upgrade, different types of problems, you know.
And you actually haven't mentioned anything about staging environments, because in the beginning you said that one of the really important things is that you have a production environment and then you want to have a testing production environment.
Sure. Yeah.
But you haven't touched it.
So just to be clear, the approach on that is that what we're doing right now is we would have a definition of the system which we would use in local development, right? Which would be a single machine with spinning all these containers up. We might then define a staging environment, which would be I don't know, a load balancer, a couple of machines, whatever, and that would be different to the production environment topology. So the topology is different in each case, but it's the same set of commands that we're running all the time, and it's the same container build process. It's just the topology is different in each case.
Yeah,
So does that make sense?
Yeah, sure.
Does the amount of crossover between this and the likes of Puppet, does that worry you guys about?
Doesn't worry us at all. We're doing this because we have a need for this type of system.
But is that maybe because you haven't explored what some of those systems?
Oh no, we have explored them. We've looked at them. They're very powerful in what they do, but they're also very complex to use, in my experience.
Sure.
I mean, you might be an expert in Puppet, I don't know. I find them very complex to use. What we're trying to get to here is a tool that's incredibly easy to use, that gives you the benefits, to allow people to take all the benefits of containerization without having to understand the complexity of Puppet and Shell. That's kind of where we're heading. Does that make sense?
No, it makes sense. I see a lot of similarities.
Yeah, but we want to make it simpler. The developer experience has to be simple, easy to use, and not complex. And I think that because we've gone from scratch looking at containers,
Sure.
because you've given them this kind of isomorphic top layer, then that's the difference between that and Puppet Chef, which is very much have to be customized for different environments. Yeah. Thank you very much, guys. I really appreciate your time.